So presently we are learning a series of advanced data structures and algorithms, and hashing is the topic which we are currently going through. In our previous lectures we have started with what actually hash function is and what are various characteristics of those hash function, and then we have started with the types of hash function, and some of the hash functions we have covered in our previous lectures. And some of those hash functions we are going to cover today. So in the previous lecture we have covered with the division method, we have seen the multiplication method, mid square method, folding method, and also the radix transformation method and extraction method. So these 6 we have already completed, and for today we are going to cover the cryptographic hash functions, then we will talk about universal hashing, and then finally we will be looking into the topic of perfect hashing as well. So with this background, let us begin with cryptographic hash functions. So when we talk about cryptographic hash functions, as the name indicates, they are designed to be used in cryptography, which is kind of altogether a separate field in computer science domain. And as far as cryptography is concerned, that is all about securing the communications, securing the messages. So these cryptographic hash functions are actually designed to be kind of very secure. What are the examples under this category are SHA-1, then they have SHA-256, SHA as in SHA-1 and then SHA-256 and then MD5. All these are designed to be very secure, and they are mostly used in cryptographic applications like blockchain. Yeah, blockchain also uses SHA-256 and so on and so forth. Coming to the particular characteristics of cryptographic hash functions, first of all they are pre-image resistance. What is pre-image resistance? That we have covered in our previous lecture. Then not only the first pre-image resistance, they are also resistant to the second pre-image, and also they are kind of collision resistance, and this is what the property which we generally look for in any type of hash functions. So going to the advantages, we can say they are highly secure, but the other side of the coin says the disadvantage is they are computationally very intensive. That means it is they take a lot of power, lot of computing resources, I can say, in order to get themselves calculated. But yes, on the other side they provide you the high security. So this was your cryptographic hash functions. Then within the types of hash functions we have two more topics to be covered. One is universal hashing, another one is perfect hashing. Now why I am not saying universal hash functions? Because when I am talking about universal hashing, I am referring to a family of hash function. I am not referring to a particular hash function, I am referring to a family of hash functions instead. And that family of hash function is kind of used in order to minimize the chances of collision for any given set of inputs. And what kind of these universal functions, what is going to be the format of these universal functions is h of k is equals to a multiplied by k plus b whole mod p then whole mod m, as it is written on the screen. So h of k is equals to a dot k plus b mod p and then whole taken as mod m. Now what does this p, a and b here are? So m, you all are aware that that is going to be your size of the hash table. A and b are nothing but randomly chosen constant, and p is a prime number which is chosen as that it should be greater than m, and which is the table size, and key k obviously is the key. So this is kind of one of the universal universal hash functions, or it is one of the hash functions which is belonging to the family of universal hashing. Coming to the advantages, as I have told you, in the starting of this universal hashing is they reduces the probability of collision. That means the chances of collision for the any given set of inputs is kind of very low. We cannot say that there are no chances of collision, because then it's going to be a perfect hash function, but it always reduces the probability of collision. On the similar lines of the disadvantages, it requires more computation and storage. Now, when we talk about the class of hash functions, we say that let us say we have that class of hash functions to be denoted by capital H, and this H be the class of functions from a set of keys to a hash table of size T size. So, that means, that essentially means that we are going to apply that H functions onto a key, and the result which is going to be our hash value or hash code will be sum of kind of any of the value among the T size. So, from 0 to T size minus 1, T size is the size of the table, size of the hash table, which is also denoted by using the variable m. Now, in this situation we can claim that, or we can say that H is universal if for any two different keys x and y from the set of keys, the number of hash functions in the class of hash function for which h of x equals to h of y equals to mod of h divided by T size. So, that means we are going to take any two different keys, and these two different keys are x and y, and we have a class of universal functions, and that class itself is denoted by h. That class H is having various functions which are denoted by small h. So, we can say h1, h2, h3, h4, all these are the hash functions which are belonging to this capital H, which is a collection, which is a class of these functions. And then when we are going to calculate the hash code or hash value for these two different keys, which are nothing but x and y. So, h of x is going to be equals to h of y, that is going to equals to mod of h divided by T size. So, if this property is going to be kind of satisfied by any of the class or any of we can say the functions which are belonging to a particular class, that class we can say is going to be your universal hash functions. And if we talk about what kind of format these universal functions is going to have, so we have just seen now we can see that technical format of writing that thing. So, here it is written on the screen, we have capital H, which is the class, is equals to h of a comma b with k colon h of a comma b with k is equals to a k plus b mod p mod T size. In the earlier version we have called it as mod m is nothing but the T size, where a and b are any randomly chosen constants which are greater than obviously 0, but are less than p, and p is actually kind of a prime number which is going to be more than the total number of keys. So, if we have such kind of an arrangement, then we will say that yes, we have a universal class of hash functions, or we have universal hashing here. Now, the question next which comes up is when do we need to use this universal class of hash functions, because on the contrary this is very computationally intensive and we have the simpler functions. For example, division, modulo division is one of the functions which is very simple, or even your mid square function or extraction or folding, they are kind of we can say very less computationally intensive, while if we talk about any cryptographic hash function or universal hash functions for that matter, they require more computer resources. So, when we talk about the universal class of hash functions, it is kind of it is to be used when very little is known about the keys. So, for example, if we take the kind of extraction method we are aware that extraction method is to be applied on those kinds of keys in which a very kind of little portion of the key is going to differ. So, for example, let us say ISBN number for a particular publisher. So, let us say it is starting from 1133. So, whatever books will be published by that publisher, ISBN number of all those books will start from 1133. So, the significant portion of that ISBN number which is going to differ will start obviously after these 4 digits. So, this is an information which we have about the keys. So, in that type of situations we really need not to use your universal hash functions. Universal class of hash functions can be used or it should be used when there is very little known, very little is known about the keys, you have very little information about the keys. When we talk about this universal function, so a class of function we can say that it is universal for any sample when a randomly chosen member of that class will be expected to distribute the sample evenly. So, whatever function you are going to use, so for example, you are using H1 or maybe you are using H2 or maybe you are using any H for that matter. That's a randomly chosen function among that class, and we expect that hash function to distribute all the samples evenly within your table. What will happen if the samples are distributed evenly? The advantage here is going to be that the probability of the collisions will be very low. So, by distributing the samples evenly, the member of that class guarantee the low probability of collisions, and which what probability we are going to say that it is kind of a low probability. So, the low probability is actually 1 divided by m or 1 divided by t size. So, when we sum up this universal hashing, we can say that H is universal if no pair of distinct keys are mapped into the same index by a randomly chosen function H. So, whatever functions are available, we are going to choose any function randomly, and by using that function no pair of distinct keys are mapped onto the same index with the probability equals to 1 by t size. So, that means the probability of collision is is less than 1 upon t size or 1 divided by t size. So, if 2 different members or any randomly chosen members of this H class are going to satisfy this property, then we can say that yes, capital H is a universal kind of hash functions, we can say. Moving on to perfect hashing. As the name indicates that the hash function here should be perfect. So, perfect in what terms? So, when we say that perfect, that means we are aiming to create a collision free hash function for, let us say, a static set of keys, and it guarantees that no 2 keys will hash to the same value. But please remember here that the set of keys is actually static. So, perfect hashing aims to create a collision free hash function for a static set of keys, and it is going to guarantee that no 2 keys will hash to the same value. Now, there can be 2 different types of this perfect hashing. One is the minimal perfect hashing and another one is the non-minimal perfect hashing. So, minimal perfect hashing ensures that the range of the hash function is equals to the number of keys, while non-minimal perfect hashing ensures that, or it says that the range may be larger than the number of keys. So, obviously, we will be looking for one which is going to give us a less amount of storage space wastage. Then coming to the advantages as indicated in in the definition, that they are perfect hash functions. That means we are assuming, or they are they are not generating any collisions. While the similar disadvantage that they are complex to construct, it is not an easy job to construct a hash function which is kind of which gives you a scenario, or which generates a scenario of perfect hashing, because perfect hashing creates a collision free hash function, and collision is something which is kind of, we can say, is unavoidable, but still we try to minimize the probability up to the extent minimum. Now, with this types of hash functions, we have seen various hash functions. Since 2 lectures we have seen division method, in which we are just going to take modulo m. Then we have seen our mid square function, in which we will be taking a constant, multiply that key by a constant which lies into 0 and 1. We have seen folding method, in which the key is actually segregated into different parts, and then it is kind of folded or twisted, and then it is processed. Then we have seen extraction method. We have also seen mid square method, in which we square the key, take the mid part, and so on and so forth. Moving forward, we have also looked into the cryptographic hash functions, then universal hashing we have seen, and also the perfect hashing. But one thing which is very certain is collision. So, what do we mean by collision? Collision is actually a situation when 2 or more keys can generate the same hash value, and sometimes it is going to happen. I am going to give you examples in a short while. This situation is called collision if 2 or more keys are having the same hash value, and this collision is going to occur when your more than one values are to be hashed by using a particular hash function. Let us say to the same slot of the table, your hash table, or any data structure which you are using for that matter. So, if 2 or more keys are having the same hash value, that situation is known as collision. Let us try to understand this collision with the help of a very simple example first, and then we will be moving on to kind of some complicated examples. So, let us take a hash function which is nothing but the key mod 10, the key value which we want to kind of search, or which we want to insert, is to be mod by 10, and we need to place those keys in the slot in the hash table. Now, what are the numbers, or what are the keys to hash? So, we have 22, we have 9, we have 14, we have 17, and we have 42 also. Now, looking at the first 4 values, you can easily say that 22 mod 10 is 2, 9 mod 10 is 9, 14 mod 10 4, and 17 mod 10 is 7. So, these numbers 22, 9, 14, 7 will be given their respective slots. But when your fifth number in the sequence, which is 42, comes up, what will happen? 42, when mod 10, we are going to get 2, but the slot of 2 is already filled. Now, this you can see in your on your screen. So, we have a hash table of size 10 starting from 0 to 9. So, the size of the hash table is 10. So, 22 is 22 mod 10 is 2. So, we have placed that in that slot corresponding to 2. 14 is placed in the slot corresponding to 4, and similarly 17 and 9 have taken their respective places. When we talk about the fifth key, which is nothing but 42, now 42 also wants the slot which is nothing but the slot of 2. Now, what is happening here? So, here this situation is also this situation is known as collision, because 22 has already taken that place of the slot corresponding to 2, and now 42 is also mapped onto the same position on which 22 is already kind of sitting, we can say. So here is a collision. This is what the situation of the collision is. Now let us try to explore this situation of collision in the case of, let us say, strings. So when we talk about strings, let us say we have a function which is h1, which is applied to some group of string, string group, which is group of character. Let us say it is applied to names, and it is going to return the ASCII value of the first letter of each name. So h1 of that key or h1 of that name is going to be the name of 0. Now what will happen? I mean, this is a kind of a clear cut case of collision, because all the names starting with the same letter are hashed to the same position. So all the letters, all the names starting with A will be hashed on to the same position, and so on and so forth. Now the question comes up, how can we resolve it? What is the problem to come out of this collision situation? So this problem can be solved by finding a function that is going to distribute the names more uniformly in the table, because generating or the hash values equals to the first letter of ASCII value of the first letter is going to give you a lot of collisions. All the names starting with A will be hashed to one particular slot, all the names starting with B will be hashed onto the all on the same slot, and in this way there is going to be a lot of collision scenarios. Now in order to solve that problem, let us make it a little bit tweaked. We are going to have a new function which is h2, and this h2 is going to add the ASCII value of first two letters. So h2 of name is going to be equals to name of 0 plus name of 1. We can say that yes, certainly it is better than h1, but this is also not a scenario which is going to give you all the keys or all the situations in a collision free manner. So what do we need to do? Can we improve upon this? Yes, we can certainly say that let us take an h3 which is going to be kind of starting from the first ASCII of the first letter to ASCII of the last letters. That means we are going to take the ASCII value of all the letters in the name and then add that. Now what will happen? The possibility of hashing different names to the same location, that is nothing but collision. So the possibility of collision is still exist. So whether we have taken our h1 or we have taken h2 or even h3 for that matter, none of them is collision free. Yes, the extent of collision is definitely we can say kind of is differing, and looking at this particular scenario, we can always say that function h3 is the best of the three, because it is going to distribute the names most uniformly for the three defined functions. But it is also kind of assuming, or the disadvantage which it inculcate in the scenario is the size of the hash table has also been kind of increased. Now let us say if the table has only 26 position, which is the kind of number of alphabets, then your h3 is not going to improve any scenario and it is as good as h1. So many of collisions are going to be there. So from this complete example, we are going to derive that the two factors which are very important in order to control the extent of collision is, these two factors are, one is the size of the table. More the size of the table, we are kind of in a comfortable situation, but increasing the size of the table may always lead to the better hashing. That is not a scenario. Increasing the table size may lead to the better hashing, but not always. So, one is the table size, another one is the hash function. More the complicated hash function you have, less the probability of collision is there. So, first of all, we need to have a sophisticated hash function, not the very simple hash function, and the table size, if we can have more, it is going to minimize the number of collision. Again I am saying it is going to minimize the number of collision, they cannot completely eliminate. That means collision has to be there. We need to fight with collision, we need to look into the ways of overcoming this problem of collision, which is going to be our topic in the next lecture. In the next lecture, we will be looking that what are the common ways to deal with the collision, because collision is going to be there, that is we can say that is something which is very, very certain. So, here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next lecture. Till then, take care. Goodbye.